push that rock with some math. So again, we're looking at improper integrals with an unbounded domain due to this infinity in the place of the upper limit of integration. And we have a rational function where it's 1 over x to p, and p must be positive. And I want to look at three cases: when p is a third, when p is 1, and when p is 3. Now, we already did p is 1 in the previous video. You should watch that first. And here is when p is 1. It's just, if this is a 1, we just have 1 over x, and there's the curve. And we saw that this area diverges. It really does expand out to infinity. So if we look at y equals 1 over p to the 1/3, which is the same thing as 1 over the cubed root of x, we see that this will be a larger area. I'll do it in another color. So, of course, if you put in 1, you still get 1. But what if I put in 2? Let's put in 8. Then I'll get 2 out. In the denominator, I'll have 1/2. And 1/2 is way up here. 1, 2, 3, 4, 5. I went by tenths, so there's 5 tenths. So this is a much flatter curve. I missed it. Oh, well. Okay, so it's a much larger area. Well, if this area diverges, well, then clearly this much larger red area is going to diverge. So we can conclude from that 1 over x to the 1/3 dx diverges, going from 1 to infinity, diverges. Okay, now let's look at the case when p is 3. So I'm going to be graphing y equals 1 over x to the 3rd. Well, now when I put in 8, if you put in 8 here, you have 8 cubed. That's a really large number in the denominator. It's a very tiny value here. And in fact, if I just put in 2, I get 1/8, which 1/8 is slightly larger than 1/10. So this is a much more dramatic drop and flattening out curve, and we see it's a much smaller area. Well, since it's a smaller area, we don't know if it diverges or not. This black area diverges, and it expands out to infinity. What about, that doesn't tell us anything about the smaller one. It tells us a lot about the larger area. If this is expanding to infinity, the black area, then the red area is definitely expanding to infinity. But what's the green area doing? Okay, well, we'll find out. So that means we set up a limit as some dummy variable goes to infinity. Okay, so when we put the dummy variable in place of the upper limit of integration, so we can do regular old definite integral here. So when you integrate this, we see that it's 1 over x to the 3, of course, is x to the -3. So I add 1 to the power and get it -2. Put the reciprocal out front and get a -1/2. And we're going to evaluate at 1 and c. And then after we evaluate, we're going to take the limit as c goes to infinity. So I'll put in c, and I get -1 over this 2 times that x, because of this negative power. Means x comes down here, but I'm putting in c, so it's c squared. Minus, put in 1. Well, I get a -1/2 times, or I didn't do it that way. Let's see. Well, anyway, 1 over 1 squared, which is just 1. So this double negative here gives me a plus, so a plus 1/2 here. But I still have this -1 over 2c squared here. And we're taking the limit as c goes to infinity. Now, I can bust up limits across plus signs, but the limit of a number is a number, so that my whole emphasis is right here. And we know from obvious theorem that this is going to 0. Think about it. If we put in x values, or c values, sorry, that should be a c. If we put in c values, then what is happening to -1? Well, you know what? We can kick out the -1/2 so that we don't have that complication, and we can just look at the limit as c goes to infinity of 1 over c squared. And then whatever this is, we'll add the limit of 1/2 to it, so we get that over there. So we put in c, and we're going to see what happens, and I don't have the negative anymore. I kicked that -1/2 out. Well, you put in 1, you get 1, but you put in 10, you get 0.01, because the 10 turns into 100 in the denominator, you put in 100, well, suddenly you have 1 over 100 squared. Well, that's 100 times 100, so you have 100 with 2 more zeros over it. So we see we're just getting closer and closer to 0. So this limit's going to 0, goes away, and so the whole thing equals 1/2. But that means, what that tells us is that it converges to 1/2. So we can conclude that this indefinite integral converges to 1/2. So this kind of illustrates something for us. It turns out, that doesn't prove anything, but it turns out that anytime you're looking at one of these where P is positive, that if P is equal to 1 or greater, if it's equal to 1, we've proved already that it diverges, and we can see that anything greater than 1, I need to say, that was a mess up. Sorry. Okay. Less than 1, if P is less than 1, then the area is greater. So notice when P was less than 1, when it was a third, that the area was actually going to be bigger, because we're in the denominator. So when P is less than or equal to 1, the integral, the improper integral that looks of this will diverge. But what if P is greater than 1? What if it's, 1.2, or in our case, the way we did it, 3? Well, then the improper integral from 1 to infinity of 1 over x to the p, where p is greater than 1, will converge. And this fact or theorem is called the p test for improper integrals. Math made simple. Simple math.